it's great to be here. My name's Andrew Dunbar. I'm a structural engineer out of a company called Structex, based in Christchurch, New Zealand. My background, I guess I started coming out of uni with a master's looking at post-tensioned timber or CLT steel cores. So that was kind of my first look. So that was under like Andy Buchanan and the like. So I got a really good insight there. And then worked for a few years at Structex as a junior engineer, doing a few kind of smaller timber jobs, and then took my chance at an OE to Vancouver in Canada and worked at Fasternet over there, and got heaps of experience in some cool mass timber buildings and a real insight into what they're doing over there, which was awesome. And now back in New Zealand for the last 3 years now, I suppose, and kicking on with joining back in the mass timber industry in New Zealand.
Yeah, amazing. I didn't realise that was your PhD under Andy Buchanan. That's really cool. I might.
Yeah, master's, so I'm not quite a doctor, but.
Oh, okay, gotcha.
Yeah.
You could have just claimed that, but that's all right.
I could have claimed that. No.
So, what are some of the unique challenges and opportunities designing with, say, slightly taller timber buildings? And I understand New Zealand, you might not be able to go as tall as other parts of the world, and maybe we can just describe some of the challenges as you go taller, and particularly in your region. Yeah,
I guess probably some of the big challenges I think with going taller is certainly the stiffness, I guess, of timber. It's naturally relatively flexible. I guess you see the big trees are made to grow tall, but then not made to have someone sitting at the top of them in a tree house in a gale force wind. So they move, and they do that on purpose. So that's probably a challenge with high-rise timber buildings, where you can end up with quite a lot of structure. So I guess looking back at kind of the progression of the tall buildings, kind of started with, like, there was the one in London, it's in a non-seismic area that was lots of walls everywhere. And then the likes of Lend-Lease in Melbourne, I think, was next at 10 stories, and again lots of walls everywhere, kind of the honeycomb type feature. So then moving towards like higher buildings and more towards seismic zones, I think Brock Commons in Vancouver at the 18-story student accommodation building was up there. So that one was a bit of a hybrid, where they had two concrete cores that were doing the lateral system. So I guess they're jumping that stiffness, the stiffness challenge by throwing a different material at it, but keeping the gravity structure as timber. And I know I think the one in Norway, 18 stories or so, or 20 stories, was all timber, but braces, and not so much of a seismic zone. So I guess where I'm coming to is, I think, the stiffness is difficult when you're getting really tall, without having just walls everywhere. Probably another challenge then was you're getting the big heights and the big forces, I guess, is the connections. So things start getting governed by connections pretty quickly, and sometimes can look a bit out of proportion if you get your system wrong to start with, if you know what I mean. And I guess seismic zones also add their own complexities with ductility and how you reliably achieve that, and potentially stuff like nailed connections with lots of slip and low post yield stiffness don't quite cut it so much anymore.
Gotcha. So I'm keen to pick your brain a little bit on seismic. Bear in mind that a lot of the listeners are structural engineers, but also a lot aren't structural engineers. So we might sort of speak at that level a little bit.
Yep.
So what are some of when it comes to mass timber buildings, because it's we'll start with the positives. Like on one hand, there are a lot of positives that you hear about when it comes to seismic zones. And what are they, and what are some of the features that are really helpful?
Yeah, so I guess there's certainly challenges in mass timber buildings, but there's awesome opportunities as well. And I think that's why probably I'm here and you're here, and hopefully the people listening are here. So in terms of seismic, I guess a big benefit of timber is it's light. It's like kind of strength to weight ratio is pretty good. So you're almost ending up with a quarter of the weight of the building if compared to concrete. So that's directly your seismic forces. The amount you've got to resist just to hold up the building is kind of potentially quartered. There's always a bit of unders and overs, but yeah, huge benefits there. Another kind of positive, I think, is really is not specific to seismic, but is the speed of construction. Like it's just it really can be quite fast, and that's something we really have to leverage, don't we, to get the cost the cost equation in there.
100%, and they all link together, like seismic design with the speed, particularly in manufacturing. One of the things you sort of touched on was steel. So like how timber can combine with steel as a combination, as a system to actually work. And you mentioned the idea of ductility, and how is that important for a seismic zone? And, is steel doing the work that enables the ductility in sort of a hybrid kind of way?
Yeah, sure. So I guess ductility at a high level, please don't shoot me or you other structural engineers out there, is I guess the ability for something to kind of go past a yield point or a soft breaking point or a fuse point and kind of hang on and go for the ride for as long as it can. So I guess some of this analogy would be like when you're playing with a paperclip and you bend it, you bending it is a yield point, and then for a while you can crank it back and forward, and that's the ductile zone, I guess, or the ductile behavior part, and then eventually you snap it, and that's the brittle failure. So timber itself is parts of it can have brittle failures, like a tension. You pull on a piece of timber and eventually it just snaps, and that's a very sudden failure. There can be slow failures in timber and compression, I guess, where things just kind of squash. But in general, in seismic design, we're trying to not have the timber. We don't want the timber to be the failing part, so we need something else to fail. So that's where steel comes into play, really. So it's either bending of little things like nails and screws, which can be very ductile, or it's something bigger for mass timber. Maybe it's a fully steel brace system, or a buckling restraint brace, or a seismic dissipator that's connected in there. So I quite like hybrid structures. I'd rather something had a bit of concrete and steel in it, which means the timber can remain as the gravity system, than it being completely shelved. So yeah, I'm not afraid to have purist timber buildings. I think we need a bit of a mix, and it might be better overall. There's other strategies we can do to kind of increase resilience with some of those other materials.
100%, and it makes a lot of sense. And I guess your master's was somewhat related to this topic. Now, what is the role of post-tension shear walls, and is there, what actually are they, and then what is the sort of feasibility, and when can someone think if it's right for them?
Right, yeah. So post-tension shear wall, it's a system called press lam. So it's So basically you get your big piece of CLT or a structural timber wall, and you put a big piece of steel tendon or a steel bar down the middle of it, and you stress that up. So that acts a bit like a rubber band. So as the wall can kind of rock around and do its thing, and this tendon is there to snap it back. So after an earthquake, it should be back vertical again. So along with that, then you can add some damping elements. So you have some little ductile fuses, say, so that in an ideal case, a big earthquake happens, your building rocks around, snaps back together from the rubber band tendon, and your dissipators do their thing, they form their fuses, they yield, and you go and unconnect them and put a new one in, and then your building's good to go. So my research came kind of from that, and I guess looking at steel weld cores in particular was the first kind of look at trying to get higher, where there's always a stairway core or multiple stairway cores in a building, and they're often a big group of walls because you need that for fire and everything anyway. So it's a nice big solid structure. So it's looking at post tensioning as a way to get high strength connections, I guess, and good seismic performance. Yeah.
So that's one, new technology. Are there any other new technologies, not necessarily just, material specific, that you see as coming through? Could be, modern methods of construction more generally, or anything like that, that are having a big influence in the way we build our buildings?
Yeah, there's certainly a few technologies coming. There's lots of different types of dissipators, and there's ones like Tectonus, which is a steel kind of form thing. So I did one of those in Vancouver, which has a.
Can you maybe elaborate on a dissipator and on how that works and what it is as well?
Yes.
And keen as to hear about that.
Yeah. Okay. So it's basically like a bit of like your shock absorber in your on your bike, and it's, as the earthquakes come, you attach these things to the bottom of the walls, say, so that the walls are rocking back and forward, and these things at each end are acting like your shock absorbers in the for the system. So they're taking a bit of the heat out of it and slowing it down. And that one in particular, I guess, is so you can often something has to get damaged to form a fuse. Like you don't usually get energy for free, but there are systems out there that can do dissipation with not much damage. So I guess base isolation has been around for a long time in New Zealand and Japan and the States, with lead rubber bearings and that sort of thing that deform and provide damping and dissipation. But I guess in a concrete wall, say, that's designed to be ductile, the energy dissipation in those come from the bars within the walls yielding and deforming, getting longer, and that energy that's created from deforming those bars gives you the energy dissipation. The only catch in that is when afterwards you're left with a wall or a building that is damaged and has used its fuse, I guess. So we saw that a lot in Christchurch following the earthquakes, that large chunks of the city were demolished, somewhat from insurance. We were very insured, but partly because of that damage.
I was going to ask, can you take a peek if it's a reinforced concrete shear wall? Can you really inspect it, or is it like sort of brittle cracks or something? How do you know if it's damaged or the fuse is broken?
It can be, depending on the detailing of the wall, it could be difficult, but in an ideal case, like a lab case, you'd see a big fan of cracks at the bottom of the wall. So it should be a whole bunch of distributed cracks. and that would be a good indication that that a hinge is formed there. And it'll be at a location like at the bottom of the wall that you'd expect, or at the beam column joint in the beam. Where it can be hard is sometimes a single crack could form at the very base. So there was a few of those in the Christchurch earthquakes where the wall detailing didn't allow this nice fan cracking to occur, and it just lifted up at the bottom, and it potentially fractures the bars, and then the wall comes back down again because of the weight on it, and you just see a little crack at the bottom, but you don't know that has actually fractured all the bars. So there's a certain challenge there, and but there are techniques, I guess, with scanning and drilling, and it gets a bit messy to investigate, but it's certainly it's a challenge, and that's why timber buildings are a bit easier. You kind of, everything's on the outside. You can see it. And you know that the crack or the rocking has to occur at the base of the wall, between the wall and the foundation.
Yeah. Well, we're talking, highly technical things in seismic and also mass timber. It's not taught at university, and this is probably across the board, not just for engineers. How did you go about learning? Because there's probably a big hurdle for an engineer listening right now, and they're thinking, hey, I learn concrete and steel, I want to get into mass timber, bloody hell, what do I do? Where do I start? How would you go about it, and what sort of methods?
Yeah, I guess for me, I went with the method of doing some study, doing a master's, but I was targeting, I guess, a very specific avenue that I wanted to do timber stuff, and so talking to the right people. So if anyone's out there kind of getting close to the end of their studies, there's lots of research programs around there. So that's one avenue that you can progress. Otherwise, if you're kind of in a consultancy, I guess timber's getting certainly more popular, and lots more people are talking about it from a client perspective. So probably my advice would be kind of say yes to every and any opportunity that you get. And secondly, don't necessarily wait for an opportunity. So try and create some. So even if it's within your office, you volunteer to create your carbon tracker spreadsheet or something, or you just do a carbon track on a concrete and steel building. And that often is enough to trigger the client, or even just other people in your office, to be like, hang on, so that's a lot of concrete, or a lot of emissions. So small things like that can lead to okay, let's investigate. Maybe this could be a timber beam even, and probably start small. Like don't try and make the purest timber building out there. Just switch the floors. Put a CLT floor in over the top of steel beams, just like a concrete, like a com floor that we have here, which is a steel tray you fill up with concrete. Just do that. They do about the same span. The timber's much lighter, and has other challenges with acoustics and stuff, but it can be competitive. So just start kind of small and then snowball. Yeah.
That's awesome. Thanks, Andrew. And looking forward with a bit of a blue sky hat on, what do you see as the future of timber construction and construction more generally in the next 5 to 10 years? Thinking about new tools or where things are going in terms of overall trends in embodied carbon, and take the question any way you like.
Yeah. Maybe I'll spin your question around a little bit and probably say, I guess I don't know if it's the future of timber construction, but probably the future of construction is timber, in my opinion. I guess thinking, if I had someone say that if concrete was invented today, it just wouldn't get off the ground. It takes a month to cure before you can do anything. You've got to have all this special formwork. You have to have special trucks to drive it around. It's super carbon intensive and it's slow. So it's kind of everything that timber isn't. But I also want to say we need concrete. It's good. It's good in the ground. It's durable. Let's just pick where we use it. So in terms of timber construction moving forward, I guess what I hope for the industry, or for the for construction industry, is kind of boring stuff, like super standardized beams and panels that you just fire out, that are super obvious. Like you go down to your Bunnings or whatever, and you can buy a glulam beam, and it's just super automated, so that it, with the goal, I guess, of getting costs down. I know Europe, even for us in New Zealand, sometimes it's cheaper to buy glulam from Europe and ship it over here than it is to buy it locally. It's not always the case, but that kind of doesn't make sense. Chop a tree down it and within 50 k's of you, get it fabricated, and it's cheaper to come from Europe. It's crazy. So I just want boring stuff. I want standardized connections that just work, kind of like steel and concrete have got these catalogs that have been around for 100 years or something. Yeah. Obviously longer, but it's well known in the industry kind of what works, how the contractors like to do it, what works from a fabrication perspective. So I know with timber, there's a lot of that IP out there from the suppliers, but I just want it really easy, so we're not having to reinvent the wheel all the times. And hopefully if we get to that, we get nice and cost competitive, and the more timber we get in the buildings, the better. And then we can play with the fringe architectural stuff as well. There's plenty of room for innovation.
100%. I love it. That's not boring at all. I'm an engineer as well, and that's the sort of stuff that excites me the most. If people want to find out more about yourself, Andrew, and some of the things we've been speaking about, where should they go?
I guess you could check out the Structex website and get my email off there. Have been involved in some kind of seminar series in New Zealand, and I've got one coming up in Nelson in a few weeks. Or if you've got a cool timber job, you want some design advice, then come and talk to me.